Okay, and now we're going to have a look at some interpretive rational function questions and sketching a trig function. All right, so now this is when you get given graphs and you then have to interpret them. Okay, so if I look at this first question, the graph of g dash x is given. Okay, so now this is the derivative graph. Please don't confuse it with g of x being the function. Too many people think, like when I ask you, where is the function decreasing? You go, from A to B or C to E, but that is g of x. Okay, you now have to put in your brain g dash x. So you've got to be thinking, what is this graph telling me in terms of the derivative? Okay, so let's have a look at the question. It says, give clear reasons, state at which of the marked values of x, A to f, will g of x have, first of all, its greatest value. Okay, so when I'm looking at this, I'm saying, hold on, the derivative g dash x is always above the x-axis. That means that my derivative is always positive. That means that my graph has to increase from A all the way through to f. It can only get bigger. Okay, because my gradient is always positive. So because it is an increasing function, the greatest value in the domain A to f would obviously be at f. All right, points of inflection. So the points of inflection would be where the second derivative is equal to naught. So that would mean the derivative of this. So that would mean the turning point of your g dash x. So that's at your B, C, and E. Okay, then determine whether g of x has a turning point. Now, in order for there to be a turning point, you've got to be thinking the derivative would have to equal to 0. I can see in this graph that there is no x-intercept here. So that means that g dash x does not equal to 0. It is only positive. And another reason is, remember, for a turning point, it has to go, your gradient has to go from increasing to decreasing, positive to negative, or from negative to positive. Okay, which this clearly doesn't. It is only positive. And so therefore, because the derivative is not equal to 0, there are no turning points. So just remember, do not rush into these questions. Think about what is the derivative saying to you. All right, another nice interpretive question that came from a couple of years ago is this. This equation was given, this rational function. So you've got a trinomial in the numerator and a trinomial in the denominator. And it says, for which values of p will the graph of f have one x-intercept, one vertical asymptote, and an oblique asymptote? Okay, so let's go through this. So let's start with the first question is a 1 x-intercept. So straight away, the first thing I always do is I factorize my numerator. Okay, it just makes so much more sense. All right, now for me to have one x-intercept, that means that I should only have one bracket upstairs and not two. At the moment, I've got two x-intercepts. So for me to have one of these brackets must cancel with a factor in the denominator. Okay, so let's have a look at this. We can either have two options. We could either have where this trinomial is factorized so that x plus 1 is a factor, which means that then those x plus 1s cancel, and I'm then left with just my 1 x-intercept. Or the factor of 2x minus 1 is able to cancel, and I'm only left with that bracket of x plus 1. So what would make, if this is equal to x plus 1, what would this one have to be? And we're just going to do it by inspection. So you're going to say, okay, well, the first and the first has to be x squared, and the last has to be 4. So if this is 1, that's got to be 4. Now remember that p would be the sum of my inners and my outers, okay? And so you've got your 4x plus your 1x, so p is equal to 5. All right, or if I wanted my factors of 2x minus 1 to cancel, so that I'm left with just that bracket, then first times first, have to get x squared. So if that's 2x, then that's got to be x over 2. And then minus 1 times what has got to give me plus 4, negative 4. Get my inners and my outers together and collect them, and I get p equal to negative 17 over 2. Okay, so you just have to think what would make one x-intercept. So now the next part was what would make one vertical asymptote. So obviously this scenario is also going to give me one vertical asymptote, because if those brackets cancel, I'm left with a denominator of x plus 4. I'd have a vertical asymptote at x equals -4. So p equals 5 is definitely an answer. And the same with this side. Okay, if 2x minus 1's cancel, I'd be left with a single factor in the denominator, which means that I'd have a vertical asymptote there. But the other option is if I can factorize the trinomial, the denominator, so that it is a perfect square. And because I've got plus 4 here, I could actually, just by inspection, the square root of 4 is 2, I could say that I could factorize this into either x plus 2 squared or x minus 2 squared. And if I factorize it into x plus 2 squared, then p would be 4. And if I factorize it into x minus 2 squared, then p would equal to -4. All of those options would end up giving me one vertical asymptote. All right, I hope that makes sense. And I think the last question was, is there an oblique asymptote, or what value of p should there be to have an oblique asymptote? It is not possible, because what has to happen for an oblique asymptote to occur, it has to be top heavy. Okay, and the only way it can be top heavy is if I have multiplied this by p1 over x or something like that, or 1 over x squared or something like that, but it actually said the value of p. That means an answer. I mean, an actual value. All right, so not a variable. Okay, so that is impossible. All right, and then the other question I wanted to show you is what would happen if they maybe asked you a rational function where they brought in some new syllabus work, which is e to the x. Okay, so if I ask you to sketch this graph, you do exactly the same steps. You start and you go, okay, I'm going to find my asymptotes. Okay, so I start with my vertical asymptote. Now my vertical asymptote is e to the x. Now e to the x is an exponential function, and we know that an exponential function can never equal to 0. So there are no vertical asymptotes. Okay, I then look at my horizontal asymptote. It's quite tricky to get my limit to infinity in this form, but look what happens if I write it in that form. I'm going to have y equals x minus 1 e to the negative x. Now if you look at the graph, so as x tends to infinity, and if I just look at the graph e to the negative x, it looks like that. And as x gets, so it's in that shape of a decreasing exponential graph, and as x gets bigger and bigger, what's going to happen to my exponential graph? It is going to get closer and closer to 0. And so if this gets closer and closer to 0, obviously the limit as x tends to infinity is also going to get closer and closer to 0. Okay, so a decreasing exponential function, the limit to infinity is always 0. If that was e to the x, well, it would be impossible to find the limit to infinity. All right, then what's my next step? Stationary points. So to get my turning points, what do? I differentiate that. I'm going to use my quotient rule. So what do? I square the denominator. So e to the 2x. I write my denominator upstairs, e to the x. I differentiate the top, 1 minus, leave the top, x minus 1, differentiate the bottom, which is also e to the x, and I then equate that to equal to 0, which remember I only need to worry about the numerator. And so I end up with e to the x and then brackets 2 minus x. And remember, e to the x cannot equal to 0, and so I'm just left with 2 minus x, which means that the x value of my stationary point is x equals 2. What do I do to that value? I then sub it back into my original, and I get my stationary point of 2, 1 over e squared. It said without using a calculator, so I leave my y value in terms of e. All right, then the next thing is asymptotes, stationary points. Next is intercepts. All right, so the x-intercept, I look at the numerator here, and it's going to be x equals 1. So it's going to be 1, 0. My y-intercept, I put x equals 0, so I'm going to have minus 1. Remember, e to the 0 is 1. Minus 1 over 1 is negative 1, and so I've got 0, negative 1. I'm now ready to sketch my graph. So now remember that you had no vertical asymptote. You had a horizontal asymptote of y equals 0. Okay. Now, when you have got intercepts, and an intercept is on an asymptote, that supersedes the asymptote. So what you are going to do is you're going to go towards your asymptote, okay, but you go through your asymptote, it then turns, and the minute it turns, the graph gets pulled towards the asymptote again. We already know there's not another x-intercept, otherwise we would have been able to calculate it. And so this graph just tends towards 0. It never crosses again. It only crosses that horizontal asymptote at that x-intercept there. All right, so I hope that makes sense. And that's your rational functions. The last thing I want to look at is trig functions. Now, for some reason, this is in your syllabus, and yet it very seldom gets asked in the exam. I think because it is quite tedious, it's quite time consuming to write to do the full answer. But I want to show you how to do it anyway. Okay, so let's say I'm sketching the graph of this function here that has a trig function in mixed with algebra. You can see there's no tan, so there's no asymptotes, and there's no denominator, so there also are, it's not a rational function, so there are no asymptotes. So the first thing I'm going to do is I'm going to differentiate to get my turning point. And so the derivative of sine 2x is cos 2x times 2, plus the derivative of x is 1. I make that equal to 0. I get a nice trig equation that you have from core maths. And remember that when you're doing the general solution, you're going to have your angle equals plus or minus whatever you get in your calculator must be in radian mode, plus, and you think k360, but you write k2 pi. Okay, and then we want to solve for x, so we divide through by 2. And now we need to find all the possible x values that fall in my domain between minus 2 pi over 3. And I get those options. Okay, so that means these are the x values of all of my turning points. Okay, I now need to substitute these points into my original to get the y value of my turning point. But I also need to establish whether those turning points are minimum or maximum. And it's quite tricky to put this on a number line and test the gradient. So in this particular case, especially with trig, it is a good idea to find the second derivative. Okay, now if you remember with the second derivative test for a maximum, if the second derivative is positive, I always say then it comes from a happy place, which means minimum medication. So it's a minimum turning point. If my second derivative is negative, it comes from an unhappy place, and so it needs maximum medication. All right, so I hope that helps, but obviously you really are just playing with concavity there. All right, so if I look, I'm going to now test the x value. This x value, I'm going to sub it. So I've calculated the second derivative here from the first derivative, and I get negative 4 sine 2x. Okay, now I'm now going to take each of these x values and I'm going to sub it into the second derivative to check if it's positive or negative, and I'm going to sub it into the original to get the y value of my turning point. All right, so I sub it into my second derivative, I get a negative answer. That means that I'm going to get a maximum, a local maximum. So I sub it into my original to get the y value. Okay, second derivative, negative, comes from an unhappy place, therefore maximum medication required. And I do exactly the same thing for each of those remaining points. Okay, so I've got maximum, minimum, maximum, minimum. And I'm now ready to sketch and plot those points. Okay, I also, don't forget, once you've got your turning points, you then get your your y-intercept. For these graphs, you always work out your x-intercept last, because if you look at this, how do you make this equation equal to 0? You're going to have to use Newton's method. So rather sketch the graph first and see if you need to use Newton's method, because maybe it's done for you. Like in this particular case, you've got your y-intercept of 0, 0. So in other words, if I put 0 in x's place, I'm going to get the sine of 0 is 0 plus 0 is 0. And so clearly that is my x and my y-intercept if it goes through the origin. Okay, and so I'm ready to draw. And so I've got and just label all of these turning points here. Okay, and I can see that my graph I only needed to draw from minus 2 pi over 3 to 2 pi over 3. And so just label everything that you can, all turning points, intercepts, etc. Let's say this graph had maybe gone through this point here, okay, that x-intercept, then I would have had to use my Newton's method, my Newton-Raphson's method to solve this equation by finding the derivative and then making an educated guess somewhere between 0 and 1.047. Okay, but yeah, it's quite a process. Anyway, there are lots of these to practice, especially the application of the calculus. And please, guys, good luck for your exam. I hope you write well, and I hope it all goes well. Thank you.